Next, we are going to look at another application of this, and now this time explicitly solve the Brachistochrone problem rather than the geometric solution we had provided earlier, just as a sort of a warm up and as a sort of a practice on how you do these kind of things and what kind of skill sets will be required to solve extremal. Of course, you have already guessed that you will be required to solve differential equations at the end of the day. Okay, so this is the Brachistochrone problem revisited. So do you remember what kind of a cost function we had there in case of the Brachistochrone problem? Between the points at x is equal to a and x is equal to b, you have to find the path of shortest travel under the action of gravity, of course, the gravitational field, right? So what did we do? We said that, okay, let's look at this small little path here. This is just dx squared plus dy squared under root, that's the length of this segment, yeah, and this one divided by the time taken to travel that length of the segment is the length divided by the speed. So what was the speed proportional to? You can do all these scalings, right? There's this acceleration due to gravity g and all this, those are, you can normalize them, but at the end of the day, mathematically speaking, it's just this object, yeah. So essentially what you had here was square root of 1 plus y prime squared divided by square root of y dx. Yes, this is what we were required to minimize in the Brachistochrone problem. Okay. Which category does this fall under again? There's a reason why I haven't erased this part. No x, right? There's no explicit appearance of x in this problem whatsoever. So we can just find out what the Hamiltonian is and equate it to a constant and then hopefully solve for a first order differential equation. Okay? Okay. So let's see what y prime dot, what is this? L of y prime. It's just a bit of differentiation, isn't it? 1 by root y sits as it is. This fellow gets differentiated with respect to y prime. So this whole thing goes to the denominator, half root 1 plus y prime squared, and in the numerator you have 2y prime, of course. Okay, so that's y prime, L y prime minus L. So I'll just write this as 1 plus y prime whole squared. Of course, we can chop off these 2's, these pesky fellows aren't really adding anything, divided by, so I just want to have a common denominator here. So I just multiplied it by 1 plus y prime squared under root, above and below. So this is the Hamiltonian. Yes, I hope there's no mistake made in the writing of the Hamiltonian, and this has to be equal to some constant. So what about it? In the next step we can take the common denominator here, square root y square root 1 plus y prime whole squared. What do we have in the numerator? There's a y prime squared, that's also getting subtracted here, no? So we essentially have a minus 1, but I say, look, this is just a constant after all. So let's call this c tilde, so that in the next step we can just say this is equal to c, where c tilde and c are just differing in signs from each other. So this is essentially the differential equation that you have to solve. Okay. So you can square this at this point to get rid of the radicals, right? And again, this maybe we can call this C bar, so that in the next stage when we square this, we can just call that C, because I want to eventually land up with a C. So we have 1 over y 1 plus y prime squared is equal to C. So I should be a little careful now, because in the calculations, so what do we have? 1 by Cy is equal to 1 plus y prime whole squared, whereupon we can just write y prime whole squared is equal to 1 by Cy minus 1. I'll just get rid of this here and put the square root back here. Is that all right? And maybe call this 1 by C as K. So ultimately the C didn't survive. Okay, let's call this 1 by. So y prime is equal to K minus y by y. I mean, please make these substitutions, and in your notebooks you understand what this means, right? We just calling 1 by C as K and going ahead with this like this. Okay. So what should we put now? Y is equal to K sine squared theta, perhaps? Would that help? Surely worth a try. Yeah. Let y is equal to K sine squared theta. At least the right hand side would perhaps look a little nice, because K minus K sine squared theta would be K cos squared theta by K sine squared theta. So basically cot theta on the right hand side, cos theta over sine theta. Yeah. But of course we have to also find what is the derivative of sine squared theta? Sine 2 theta. Yeah. So we end up with K sine 2 theta d theta dx is equal to cot theta, right? Again, cos and cos can be taken. This is 2 sine theta cos theta. So the cos theta and cos theta can go off, and this is just 2k sine squared theta d theta is equal to dx. Yeah, I hope again the calculations are not off. I'll just carve out a little space here and hope to finish the calculation here. Yeah, so you can just write 2k sine squared theta d theta is equal to dx. So 2 sine squared theta is 1 minus cos 2 theta. Yeah. So this is k 1 minus cos 2 theta d theta is equal to dx. So if we now perform integration on this, we can do that. K theta minus k by 2 sine 2 theta is equal to x plus some constant alpha, right. So I can just put this alpha back here, maybe call this as some plus alpha here, doesn't really matter. Yeah. So this is my x and this is my y, which of course I could have also called as y is equal to half or k by 2 sine squared theta. So that is 1 minus cos 2 theta, and just like that, lo and behold, we have the parametric equation of a cycloid, right. So indeed what we had arrived at using that limiting sense refraction, the idea of refraction in the limiting case, right, and then geometrically we had seen that it must necessarily lead to a cycloid. Now we have the analytical expression for the cycloid as a solution to the Brachistochrone problem, of course using nothing other than the Euler-Lagrange equation under the special situation where there is no x explicitly appearing in your cost functional. What I would invite you to try is to solve for this using the second order differential equation, assuming that you do not know the special situation where this x is not present, and just blindly apply the y double prime condition, right, and see how far you can go with that. See, the point is differential equations, there is only a small class of differential equations that you can actually solve analytically. Must be very aware of this. All the things that are taught in classes only cater to a very limited class of differential equations of a very special kinds of structure only. So arbitrarily, if I give you a first order differential equation even, it might be quite complicated and you might not have any analytical solution, and you should be able to live with that, right. So just because an extremal exists, I want to sort of highlight this. This is not like numerically computing the optimal candidate. Even in optimization problems, static optimization problems, let us say you have to solve a polynomial of degree greater than 4 or so on, you still have to resort to numerical methods. But the complexity in the calculation is significantly more here. You are not just computing a simple point here, you are actually computing a whole curve, the solution to a whole differential equation, and you might have to actually numerically solve that. Okay, so numerical computation of optimal candidates or optimal curves is not trivial. You can see books after books on optimal control written where they actually highlight one after another computationally efficient methods to be able to solve for these problems. Yeah, of course you will not solve them in the form of Euler-Lagrange equation once you get into optimal control, but still the point remains that with this simple example itself, you will immediately see that even where a closed form solution is available, it requires a considerable amount of work. And now if a closed form solution is not available, if it is not tractable to solve analytically, the problem becomes that much more challenging. Okay, so that is why optimal control problems in general may not yield themselves very easily to a tractable solution, and you should be comfortable with that idea at least in principle. Okay, all right. I think we have a fair amount of time. So in that small amount of time, I will just derive a result which again will seem like something totally irrelevant to what we have done. Okay, so I mentioned this lemma, the Raymond-Dubois lemma. I will just try and establish what that lemma says, and perhaps those of you who are paying close attention to what I have said at the beginning of this lecture, you can actually go back after this and try to see whether you can use this lemma to prove something important, that important thing being an integral form of the Euler-Lagrange equation. Okay, so let us just state the lemma and then see how far we can get ahead with the proof of the same. So suppose you have this. Let's call this condition 1. Okay. Of course, the G has to also satisfy this, right? That's part of condition 1 already. You're not just looking at any kind of G, you're looking at those particular G's which vanish at the endpoints, like the vanishing perturbations we had considered. See, this is very uncannily similar to the result that we had the other day, except for the fact that instead of a G, you now have a G prime. So what did we have the other day? What could we conclude about phi? Phi must be 0 in such a situation if this was G instead of G prime. We've already established that. Just intuitively, what do you think should be true of phi now? What should be true of phi now? Any guesses? Should phi still be 0 like the other day? Sorry? A constant. Very good. That's a good guess. But how to establish this? How to prove this? This is the Riemann-Dubois lemma. Okay. Let's just define this object here. Sorry. Okay. So it's like the average of the function over the interval. Okay. And let's define phi tilde x as okay. What can you say is a property of this fellow here? Anything that strikes out as a property of this object? Sorry? No, that's okay. Anything else that's relevant? Integration from will be 0. Why so? Okay, let's try. Very good. I can just split it up into two parts, right? Sorry, a to b, right? Yeah, a to b dx. So, what can we say? You see, you have defined this m already. After the integration, this is just a constant, and this is just b minus a, which gets cancelled out from the b minus a in the denominator here. So, this is definitely 0. Yeah, very good, no? Okay, very good. What else have we got now? So, I've actually also defined this, so perhaps I should use this symbol to clarify that this is how it's being defined here. So, by virtue of my definitions of m and phi tilde, I have this following conclusion. Okay, now what else? Look, this is what I have to prove. Yeah, if my conjecture is correct, if this result is correct, then phi x must be a constant. Yeah. What if phi tilde is 0? If we can establish that, then we'll be done. Yeah. What can you say about phi tilde? Just think about it. Look at this object here. Which object does this remind you of with respect to G? What other special property does this enjoy? If you look at phi tilde here, what special property can you say about phi tilde here? Look at what G has to satisfy. G of A is equal to G of B is equal to 0. Does that somehow connect to anything that you can think of about phi tilde? Not necessarily phi tilde, perhaps think about its derivatives or its integrals. Anything that reminds you of this property here? GA is equal to GB is equal to 0. Sorry? Will that help my purpose? See, what I have to establish is this being 0 implies phi x is a constant. If by some reasoning I can establish that phi tilde is 0, I would be done. Yes? So, phi tilde being 0 would somehow help me. Yeah? Think about the result we had derived the other day. Okay, we'll continue from this in the next lecture. But just think about this, whatever we've written here, and I'm sure you'll be able to arrive at the result yourself before we meet next. Okay? But just think about what we are trying to achieve, that the idea is to be able to establish that this object is equal to 0. Okay? I'll leave you to think on that. When we come back in the next lecture, we shall move ahead with this and we shall show you that this result is true, and not just that this result is true, this has very great implications to what we are trying to arrive at, that is the integral form of the Euler-Lagrange conditions. Okay? Thank you.